Hey chemistry students, this is Mr. Resentis and I'm on page 66 of your book. 66. We're going through the states of matter, and you perhaps you recall we have, this is supposed to look like a beaker. Solid, liquid, gas. Plasma as well, like a flame. Flame would be an example of plasma. What's the inner core of the sun might be an example of plasma. That's another form of matter. If the particles are touching, it's a solid. If they're close but not quite touching, conforming to the bottom, then you know it's a liquid. If they're uniformly distributed, far from each other, you know it's a gas. This type of illustration comes up in standardized testing quite frequently. So you should be able to visualize the particles. It's going to come in handy whenever we talk about what does it mean for water to dissolve ions. So it's important for you to be able to visualize this. We could take this a step further, talk a little bit more about what is it? Here's a good example of a couple of different types of a couple of different ways that we find matter, and we could find matter in a homogeneous solid or a homogeneous liquid or gas. Homogeneous, because no matter where you sample this, you should get the same proportion. So you can't have you can have homogeneous compounds, but mostly we think of homogeneous as solutions. But you can't have an alloy, a metal with more than one different type of metal blended would be a good example of a homogeneous solid. But mostly we refer to a homogeneous liquid. Salt water is a good example. Homogeneous, uniform throughout. No matter where you sample it, you get the same thing. Whereas in a heterogeneous, if you sampled it, you wouldn't, and you sample it more than once, you wouldn't get the same exact proportion. You'd get there's a visibly different substances within your mixtures. Okay, so both of these would be considered mixtures, homogeneous or heterogeneous. Right? Now, matter can appear to change, and that happens when it gets broken into bits. If I took this piece of paper and shredded it and then stomped on it, mixed it with water, it appears to change, but it doesn't really change, and we call that just a physical change. So when it does that, the key point there is that it appears to change, but it doesn't really. The starting material and the ending material, after whatever it is that you did to it, If it is the same thing, it's just a physical change. Alright, now easy enough. When matter changes, physically into a new thing, when matter changes into a new thing, you start with one thing and you did something to it, and it's a new thing with new properties. You took a piece of paper and you burned it. Then you started with paper, but now you have ash. Chemically, they're different. They behave different. They look different. Then you know that you went through a chemical change. All right. So a chemical change is when the ending thing is completely different from the starting thing, and a physical change is when the ending thing is really just the exact same thing as what you started with. It just looks different. Maybe it's smaller, maybe it's bigger, but it still analyzes to be the exact same thing, so you haven't changed it chemically. Alright, so physical change and chemical change. Now, we could classify matter. Alright? Now, so matter can be classified into a mixture or into a pure substance. And we were talking about some of these mixtures earlier, right? And the mixtures that we referred to earlier could be homogeneous or heterogeneous. Homogeneous or heterogeneous, right? Now, homogeneous, such as, and a good example would be salt water. It's uniform throughout. Try and remember that. Heterogeneous, on the other hand, is not uniform. You could clearly see chunks in it. You could clearly see there's a difference. Granite's a good example. Muddy creek water, oil and water, clearly heterogeneous. Hetero meaning different. You could clearly see that there's a difference. Pure substances, pure substances come in a couple of different varieties as well. And these are important terms for us to know. We have compounds, and we have elements. Right? Compounds and elements. Those are two different types of pure substances. As I said before, no matter where you sampled it, you would get an analysis that was the exact same proportion whenever and that's how you know it was a pure substance. Whereas with a mixture, you could break it down further, and that's how you can distinguish the difference between the two. So compounds contain two or more elements. And elements cannot be separated into a more simple substance. Okay, and we're going to learn about the 90 or so elements that are naturally occurring on the periodic table, and that's what we're going to spend loads of time on. But the point is that we have this list of things that you cannot separate it into something more simple, and we just so happen to call it an element, and we'll talk more about those elements later. So what I'll do is I will give you an assessment like this to ask you whether this is a solid, liquid, or a gas. Is it made up of compounds, pure substance? Is it heterogeneous? Is it homogeneous? And these maps, what we call little matter maps, what they do is they illustrate, they could illustrate what's happening within a solution, a solid or a gas, and it gives you an idea of what does it mean for something to be dissolved, or what does it mean, and it'll be helpful later whenever we discuss things like dissolving an ion in water. What's happening, and why does it behave the way it does? Here, clearly, we have a solid, and they're all exactly the same. So these are clearly elements. It's a pure substance. It's homogeneous, and you'll see this. You'll see this in class.